Okay, welcome back. Today we're going to look at Chapter 2, which is motion in one dimension, kinematics in particular. What is kinematics? It is the empirical study of motion. It's a study of motion basically ignoring the causes of the motion, just looking at motion, trying to find things that fit, the mathematical equations that fit the motion. Kinds of motion we can have in physics is translation, which is one-dimensional motion, say along a x number line, either positive or negative. Rotation, which is circular motion along some kind of arc. Or vibration, which is repetitive motion about some kind of equilibrium point. At some point, we're going to look at all three of these motions, but for now, we're just going to focus on translation. To look at kinematics and the study of motion, we need to define some new variables. And the first variable we're going to define is called displacement. By definition, we define displacement, a change in our position, delta x, is as our final position minus our initial position. And that's what this triple equal sign represents. It's not necessarily an equal sign, it is a definition. So it is stronger than an equal sign. It is exactly a definition of what we mean. And our displacement is our final position minus our initial position in a value of x. So we could have a one-dimensional displacement, and we could go to a final position that is a positive position. In other words, could be greater than our initial position. Or we could go in a negative direction. Maybe our final position is less than our initial position, or negative as we define our position. Our position could be positive or negative along this number line, this one-dimensional line. And our displacement then could either be positive or negative as well. For displacement, the path that we actually take, going from our initial position to our final position, doesn't particularly matter. Only the initial and final positions matter. So as I'm taking a path from my initial position to my final position, how I got there, as far as displacement goes, doesn't matter. All I want to know is what my final value is, my final position, and what my initial value is, my initial position. The length of the path we traverse in going from our initial position to our final position is what we call the distance traveled, and that will always be a positive quantity. So let's use an example. Let's say I start at position 0 and I move over to position 5 meters. My displacement would then be my final position 5 minus my initial position 0, and my distance traveled would be 5 meters as well. But let's say I start at 0 and I traverse to a position of a negative 5. So then my final position would be a negative 5, my initial position would be 0, and my displacement would be a negative 5 minus 0, or a negative 5 meters. My distance traveled in that case would actually be a positive 5 meters, because distance traveled will always be a positive quantity, and it will just be the length of the path that you traveled, while displacement is always your final minus your initial position. So they are different. The only time that the two would actually be the same is if I traveled in a straight line direction in a positive direction. Then my distance traveled and my displacement would exactly be the same. And that happens quite a lot, so that's why we get the two confused as far as a distance and a displacement. But in physics, they can be different. So in the particular case, straight line motion, distance and displacement would be the same. So once we accept this idea of displacement, our final position minus our initial position, we can then describe our other quantities as well. We will describe what we call average velocity, a v with a bar over it, as our displacement over our interval of time, change in time. So displacement per time is average velocity. Or I could write it like this. My average velocity, v with a bar, is my final position minus my initial position over my final time minus my initial time, my interval of time. Now with this definition of average velocity, if I look at this equation, v bar is equal to delta x over delta t, multiply both sides by delta t, I could get that my displacement is equal to my average velocity times my interval of time, delta t. This could be quite useful in some of the things that are yet to come. So let's try an example. Here's a graph. It is a graph of displacement versus time. So on the abscissa we have displacement, on the ordinate abscissa we have time, on the ordinate we have displacement. So we're showing displacement versus time, and this could be a motion time graph similar to what we normally do in our lab number 1. So I want to find for the average velocity over the various time intervals. First one starting from 0 to 2 seconds. All right, so I'm looking at this graph, and if I go from 0 to 2 seconds, my initial position is going to be 0 at t equals 0, and my final position is going to be 10 meters at t equals 2 seconds. So essentially, for my average velocity, I'm looking at the slope of the line that connects those 2 points. Since I'm really only interested in my final and my initial positions, I'm looking at the line that connects those 2 points. My average velocity will be my change in position or my change in time, which will be my final position minus my initial position over my change in time, my final time minus my initial time. That'll be 10 meters minus 0 over 2 seconds minus 0 seconds. 10 divided by 2, 5 meters per second, positive. That's the slope of that line that connects those 2 points on this position versus time graph. What about from 0 to 4 seconds? I want to find my average velocity on this position versus time from 0 to 4 seconds. Now, if I were to actually do this graph in my motion, I'm starting at position 0 at t equals 0. I travel 10 meters over 2 seconds, and then for the next 2 seconds, I travel back another 5 meters. So I'm going a total distance of 10 plus 5, 15 meters, but I end up at a position of x equals 5 as opposed to my initial position of x equals 0. So if we're calculating our average velocity, we want to just know our initial and final positions and our time interval, and how we got there doesn't really matter. So our initial position is x equals 0, time t equals 0. Our final position is x equals 5, t equals 4 seconds. Our average velocity is our change in position, our final minus our initial, 5 minus 0, over 4 seconds. We have an average velocity of 1.25 meters per second, which happens to be the slope of that line that connects those 2 points. So that is our average velocity. What would be our average speed, though? Speed is our total distance traveled over our time. And in this case, our total distance traveled was the 10 plus 5, 15 meters, divided by 4 seconds. So we have 15 meters covered in 4 seconds. That would be 15 divided by 4, 3.75 meters per second. So we have an average velocity of 1.25 meters per second, but we have a speed, average speed, of 3.75 meters per second. So they are indeed different. What about from 2 seconds to 4 seconds? I'm looking at the slope of this line. My initial position is 10 at t equals 2. My final position is 5 at t equals 4. So So my average velocity is my final position minus my initial position, 5 minus my initial position of 10 over my interval of time, 4 seconds minus 2 seconds. So I'm going to get a negative 5 divided by 2, or a negative 2.5 meters per second. My velocity in going from 2 seconds to 4 seconds is a negative 2.5 meters per second. And hence I was going from position 10 down to position 5. I was going in a negative direction, hence I had a negative velocity. What's my speed? My speed would be my distance covered in my time. In this case I covered 5 meters and did it in 2 seconds. So my speed would be 2.5 meters per second, a positive value, while my velocity, average velocity, is a negative 2.5 meters per second. So velocity could be positive or negative. It depends on direction, where speed is a scalar quantity. It just depends on my distance per time. From 4 seconds to 7 seconds, again, my initial position, x equal 5 on this graph, at t equal 4 seconds. My final position, if I look at this graph, will be x equal to negative 5, t at 7 seconds. My average velocity is my final position, negative 5, minus my initial position, 5, over 3 seconds. That would be a negative 10 over 3, or a negative 3.3 meters per second. And then from 0 to 8 seconds, my initial position is 0. My final position is 0. My average velocity is 0. Because even though I traveled 10 meters this way, came back 5 meters, stopped for a second, went 10 meters to negative 5, came back 5, I end up where I started. So my final position is the same as my initial position. My change in position is 0. My average velocity is 0. What's my average speed over this interval? Well, that's different. I went 10 meters, then 5 meters, stopped for a second, went another 10 meters this way, and then came back 5 meters. So I went 10 plus 5 plus 10 plus 5, 30 meters, and I did it in 8 seconds. So 30 meters divided by 8 is 3.75 meters per second. So I had an average speed of 3.75 meters per second, but my average velocity was 0. Okay. Let's try another example. Let's say I know that Birmingham is 100 miles away. And let's say I travel down to Birmingham at 50 miles per hour. So I know it's going to take me 2 hours to get there. And let's say I turn around once I get down to Birmingham and I travel back to Decatur at 100 miles per hour. And somehow I avoid not getting a ticket. So it took me an hour to get back. So the question is, what is my average velocity? And what is my average speed? Let's answer the second one first. What's my average speed? Well, strictly speaking, my average speed is my total distance covered divided by my total time. So if I went down to Birmingham 100 miles away, came back 100 miles, I actually covered 200 miles, and I did it in 3 hours, because it took me 2 hours to get down there at 50 miles per hour, and it took me an hour to get back at 100 miles per hour. So I went 200 miles in 3 hours, giving me an average speed of 66.7 miles per hour. So even though I went down at 50 miles per hour and came back at 100 miles per hour, my average speed is not 75 miles per hour. It is 66.7 miles per hour, and that's because the intervals of time for each trip were different. If they were the same, then I'd be okay. My average velocity in going down to Birmingham would be 0, because I came back and my final position is the same as my initial position. So I have an average velocity of 0, but but an average speed of 66.7 miles per hour. So if I did get picked up by the police along the way and they asked me, do you know what velocity you were going at? And I could say 0. And you can't get me on that. At least hopefully not. Maybe they'd put me in jail for that, just for talking back. So we have defined displacement and average velocity. We're also interested in instantaneous velocity. If I took the limit of my displacement in an interval of time where that interval of time approaches 0, so I'm looking at the infinitesimal displacement dx in an infinitesimal amount of time dt as I'm approaching a moment, then that little change in position in that very little change in time at that moment will give me my instantaneous velocity. So dx dt is my instantaneous velocity. I could look at this in terms of calculus. That means the derivative of my position as a function of time is my velocity. Let's try this out. Here's another position versus time graph. And on this one, we have ourselves a parabola described by the expression x equal negative 4t plus 2t squared. X is in meters, t is in seconds. This position versus time graph for this motion is shown in this figure. X on the vertical, t on the horizontal. Calculate the average velocity in the time interval t equal 1 second to t equal 3 seconds. All right, so we're going to go from 1 second to 3 seconds. X is equal to negative 4t plus 2t squared. At t equal 1 second, I can calculate what my initial position is. That's going to be negative 4 times 1 second plus 2 times 1 second squared, which would be negative 4 plus 2, or negative 2. Or I could have looked at the graph and seen that on the graph at t equal 1 second, I'm at x equal negative 2. My final position at t equal 3 seconds is a negative 4 times 3 plus 2 times 3 squared, which will be a negative 12 plus 2 times 9, 18, or 6. And again, I can look at the graph and look over here at t equal 3 seconds, my position is 6. So it's a good graph. So here's my initial and final positions. My average velocity is my final position minus my initial position over my interval of time. So this will be 6 minus my initial position of negative 2. So that'll be 6 plus 2, 8, divided by 2 seconds, or 4 meters per second, which happens to be the slope of that line that connects those 2 points, rise over run. All right, so that's the slope of that chord between those 2 points on this graph. Let's calculate the instantaneous velocity at the time t equal 2.5 seconds. To calculate instantaneous velocity, one way to do it graphically is to imagine what we just did, where we had 2 points on either side of the point in question, and we had a chord connecting those points. If I reduce my time interval down, down, down until that chord approaches that point, there will be a point where I'm at that instant where my time interval is infinitesimally small, minute. And my chord has reduced down to the point where it's only intersecting at that point, at one point. So I'm looking at the tangent line that contacts my graph at that particular point. If I can find the slope of that tangent line, that will be my instantaneous velocity at that point. So graphically, I've already done that here. I got a line that intersects at 2.5 seconds, and it's a tangent line intersecting only at that point. I want to figure out the slope of that line to get my velocity. So I want rise over run. And to figure out rise over run, I'm looking at another point on this line. I have x equal 8 and t equal 3.5 seconds. And then another point down here, x equal negative 4, t equal 1.5 seconds. So my change in x will be 8 minus a negative 4, or 12. My change in time will be 3.5 seconds minus 1.5 seconds or 2, and hence my rise over run, which will be my instantaneous velocity in this case, 12 divided by 2, or 6 meters per second. That's the slope of that line. That is my instantaneous velocity. Another way I could find my instantaneous velocity is to take the derivative of my position. And my position was described as negative 4t plus 2t squared. So the derivative as a function of time of that, if I take the derivative of a negative 4t, I'll just get a negative 4. And the derivative of 2t squared, decrement the power, I'll get 4t. So my velocity for all time is a negative 4 plus 4t. At the particular time of t equal 2.5 seconds, I'll have a negative 4 plus 4 times 2.5. That's a negative 4 plus 10, or 6 meters per second. By golly, the two match up. I wouldn't necessarily expect that because the graphical technique is not purely exact. I mean, there's so many ways I could draw that graph and be a little bit off, whereas the derivative technique is exactly correct. Okay, so far we've defined displacement and we have defined velocity. There's one other variable that we need to define, and it's called acceleration. And acceleration is our change in velocity and our change in time. And the average acceleration is delta change in velocity, our final velocity minus our initial velocity, in some interval of time. Instantaneous acceleration would be where we reduce our time interval infinitesimally small down to a moment. And as we do that, the limit of our change in velocity as we do that would be our infinitesimal change in velocity in an infinitesimal amount of time, dv over dt. Or I can even think of that as the second derivative of our position as a function of time. That is our instantaneous acceleration. If the acceleration is constant, and then the instantaneous acceleration will equal our average acceleration, or we'll have our instantaneous acceleration equal to acceleration bar, which will be our final velocity minus our initial velocity over the interval of time. For the purposes of this course, we're only going to deal with constant acceleration. So this will always be true then. Our instantaneous acceleration will equal our average acceleration, which will equal a constant. We will only concern ourselves with problems of this type. There are problems where the acceleration can change, and there's a term for when the acceleration changes as a function of time, and that's called the jerk. But we're not going to deal with that in this course. We're only going to deal with constant acceleration. So let's try a problem. An object moves along the x-axis according to the equation x equal 3t squared minus 2t plus 3. Determine the average velocity between t equal 2 seconds and t equal 3 seconds. So we have this equation, x equal 3t squared minus 2t plus 3. We want to find the average velocity between t equal 2 and 3 seconds. First of all, let's find the velocity for all time. It's the derivative of the position as a function of time. Oops, I'm a little bit ahead of myself. Looks like I found a different way of finding the average velocity. Let's find our position, initial and final, and then do that over our interval of time. So we'll do that first. At t equal 2 seconds, we have 3 times 2 squared minus 2 times 2 plus 3. That's 11. And our final position will be 3 times 3 squared minus 2 times 3 seconds plus 3. That's going to be 3 times 9, or 27, minus 6 plus 3, or 24. So there's our initial and final positions respectively. So our average velocity will be our final position minus our initial position, 24 minus 11, over our time interval, 3 seconds minus 2 seconds, or 1 second, 13 meters per second. Nice to know. So that's our average velocity. I want to find our instantaneous velocity as well, taking our position and taking the derivative of that. That will be our instantaneous velocity for all time. The derivative of 3t squared minus 2t plus 3, derivative of the constant 3 is 0, derivative of minus 2t will give us 2, and derivative of 3t squared will give us 6t. So we have that the velocity is 6t minus 2. At the particular times of 2 seconds, that velocity would be 6 times 2 seconds minus 2, 12 minus 2, or 10. And at the particular time of 3 seconds, our velocity would be 6 times 3 minus 2, 18 minus 2, or 16. Those will be our instantaneous velocities at those respective times. Note that if we're under constant acceleration, we can average our velocities to get our average velocity. So in other words, if I have 10 meters per second at my first time, and at my final time, 16 meters per second, my average velocity will be 10 plus 16 divided by 2, or 13 meters per second, just like what we found using our change in position over our change in time on the previous screen. That is only true if I have constant acceleration. So it didn't work in my example where I went down to Birmingham at 50 miles per hour and came back at 100 miles per hour. The reason it didn't work on that example is because I didn't have constant acceleration. When I went down to Birmingham, I turned around and came back, and because I turned around, I didn't have one interval of time of constant acceleration. I changed my acceleration at that moment and came back, and that all bets were off at that moment. In this case, my average acceleration at between 2 seconds and 3 seconds is my change in velocity over my change in time. 16 minus 10 over 1 second is 6 meters per second squared. My instantaneous acceleration, I have to take the derivative of my velocity, that's a function of time. Since my velocity is 6t minus 2, if I take the derivative of that, I get my acceleration. The derivative of minus 2 is going to be 0 because it's a constant. The derivative of 6t will just give me 6. So my acceleration is 6 meters per second squared. And I can see from this example that my instantaneous acceleration is the same as my average acceleration. So I did indeed have constant acceleration. Okay, so that concludes our first short lecture in Chapter 2. All we've done now to this point is define our kinematic variables. And we want to define these various variables well because in our next video we're going to use them in some very neat equations called the kinematic equations. So stay tuned and get ready for the next video.